So for example, 4, that's to find the eigenvalues and the corresponding eigenvectors. So notice the singular, plural, depending on the case. You'll see why in a second. So what do we do? For to get the eigenvalues, we set the matrix A. Okay, let A minus lambda I and find the determinant of it and set it equal to 0. In other words, have to do, guys, is subtract lambda to the elements along the main diagonal. All right. And well, that is the determinant of 3 minus lambda, -9 minus lambda. Those are the elements that get subtracted by lambda. The other two elements just remain the same. And let this be equal to 0. Okay. So let's evaluate the determinant. 3 minus lambda times -9 minus lambda, and then minus, but well, minus a negative, that's actually a positive. 18 times 2, is that 36? Okay, let me continue here. So 3 times -9, is that -27? 3 times negative lambda, that's -3 lambda. And then negative times a negative is positive, 9 lambda. And negative times a negative, it's positive lambda squared plus 36, and set this equal to 0. Keep setting it equal to 0. All right. So let's simplify the equation to get lambda squared. Plus 3 lambda. Wait, actually plus 6 lambda, not 3, plus 6 lambda. And then 36 minus 27, is that equal to, what is that? 6. Wait, yeah, 6. No, 9, right? Plus 9. And let that be equal to 0. So factor the polynomial. Factors of 9 that are to 6 have about plus 3 and plus 3. Let it that equal to 0. Well, actually, do you see how we have a repeated eigenvalue? It's only one. It's a value that equals to -3 of multiplicity 2. All right? So, well, let's get the corresponding eigenvector to lambda equals to -3. All right. Well, so for lambda equals -3, what do we do? Set the equation a minus lambda I times some vector v equals to the 0 vector. Solving this system of equations, it's going to give us the eigenvector corresponding to the eigenvalue of lambda equals -3. All right. Well, so here's the thing. Subtracting -3, isn't that the same as saying plus 3i? V equals to 0. Okay, turn this to a system of equations. So what are we doing? Every time you add or subtract 3 times the identity matrix to another matrix, all you have to do is the operations on the main diagonal as we did here. All right. So that is A, which is 3 plus 3, and then -9 plus 3. The other two elements, 2 and -18, remain the same. That's times a vector, some vector that I'm going to call v1 and v2. Okay, that's actually the corresponding eigenvector. We're looking for the eigenvalue here. And let that be equal to, oh, the 0 vector, not just equal to 0, the 0 vector. Because this is a vector equation. A vector equation, well, technically a system of equations, isn't it? Well, so simplify this, and if it works for you, wait, 0, 0 instead. If it works better for you guys, write this in terms of an augmented matrix. It's a more compact notation. 3 plus 3 equals to 6, and -18 remains the same. 2 remains the same. 3 minus 9 is that -6. And with a bar, 0, 0. That's how we denote an augmented matrix. It's a more compact, more convenient notation. Okay? Now, here's the thing. Every time we solve this kind of problems, it's almost always the case where one row of the matrix is a multiple of another. So you don't have to. spend any time reducing the matrix. I mean, if you want to do it, that's fine. If you want to divide all elements along all, I mean, the first row by 6 to get a, what is that, 1, -3, go for it. I'm going to do it, okay? So this is the same as saying, what is that, dividing by 6, that is 1/6 row 1 to obtain a new row 1, and how about 1/2 row 2 to obtain a new row 2? That's going to leave us with 1, -3, and 1, also -3, right? 0, 0. And well, from here, how do we get the eigenvector? So choose any of the rows, your favorite one. I mean, it's the same one, right? I'm going to highlight it. I'm going to highlight it, and I'm going to write the corresponding equation to this. Again, what do we do when we write a system of equations into a matrix? We are encoding the system of equations into a matrix. Now that we have a reduced matrix, let's decode the matrix back into a system, a more simplified one, where in this case this would be the coefficient of x or the coefficient of y and the coefficient of y. However, we're not working with x's and y's. We're working, our variables here are v1 and v2. So let me write the equation: 1 times v1 plus, or rather minus, 3 times v2 equal to 0. So v1 equals to 3 v2. Well, because of the nature of the solution to the system, the system has infinitely many solutions. Okay, so for the sake of simplicity, let v2 equals to 1. I mean, you can whatever you want. However, keep it simple. Keep it simple. Let it be equal to 1. In some cases, we may need to let that v2 be a whole nother number. We'll figure it out. We'll talk about that later. So letting v2 equals to 1, that means v1 equals to 3 times v2, which is 1, which equals to 3. So the eigenvector will be v equals to v1, v2, that is the vector 3, comma 1. So that is the corresponding eigenvector. Now, when it comes to getting what's it called, repeated eigenvalues, well, there's a way to get a second eigenvector because, I mean, this is a 2 by 2 system, so we need to get two different eigenvectors. However, because we only have one eigenvalue for now, that's what we're going to do. When we get to solve these systems of equations, we'll show you what we're going to do when we have repeated eigenvalues. In the meantime, let's have a look at example number 5. All right. Example number 5. Find the eigenvalues and the corresponding eigenvector of matrix A. All right. So A minus lambda I equals 9 minus lambda, 5, -1, and 7 minus lambda. Okay. Now to solve, let's find the determinant. 9 minus lambda, 7 minus lambda, -1, 5. Let that be equal to 0. That's to get the eigenvalues of the matrix. All right. Again, product along the main diagonal, elements along the main diagonal, 9 minus lambda times 7 minus lambda, plus, in this case, because minus and negative, 1 times 5, that's plus 5. Let it be equal to 0. Okay. So 9 times 7, is that 63? And 9 times negative lambda minus 9 lambda minus 7 lambda plus lambda squared plus 5. Let that be equal to 0. Keep simplifying the equation. By the way, this equation is called the characteristic equation. That's the equation that calculates the eigenvalues for us. So that's lambda squared. What is that? So lambda squared minus 16. No, yeah, minus 16 lambda, and 63 plus 5, is that 68? And let that be equal to 0. Okay, guys, now that we have a polynomial, is this factorable? Can we find factors of 68 that add up to negative 16, guys? Can we have any? What do we do in this case? Quadratic formula. So lambda equals to 16 plus or minus the square root of 16 squared minus 4 times 1 times 68. Everything divided by 2 times a, which is 2 times 1. That is 16 plus or minus the square root. Simplifying all this number inside of the radical should give us a negative 16. Okay, I'm not going to do all the steps. Come on, it's quadratic equations, right? So everything divided by 2. Okay, well, we still need to simplify that square root of negative 16, which will be lambda equal to 16 plus or minus 4i over 2, which reduces to 8 plus or minus 2i. All right? So in this case, the eigenvalues and the eigenvalues are actually complex numbers. All right? Well, how do we work with these complex eigenvalues? Well, we work them the same way, right? I mean, subtract the elements along the main diagonal of the given matrix, subtract the eigenvalue, and do the work, okay? Yes, it's gonna look crazy for a second because of all the terms we're gonna have in this big matrix, but I mean, it is what it is, okay? It's what it is. So for lambda, 1 equals to 8 plus 2i. Okay, what do we have? Number 1, this will be, so a minus 8 plus 2i times the identity matrix times the vector we're looking for, which is the eigenvector. Let that be equal to the 0 vector. Okay, so to subtract 8 plus 2i to the elements along the main diagonal. Just like actually we have it in a way pre-set it up, right? So that'll be, okay, that means who? Big matrix. 9 minus 8 plus 2i, and then 7 minus 8 plus 2i. The other two elements remain the same, negative 1 and 5. This is times the vector v1, v2. Let that be equal to the 0 vector. All right. Okay, let me keep writing this one as a matrix. However, I'm gonna write it as an augmented matrix, so I don't have this multiplication of vectors. I mean, we could do the multiplication. That's fine. But I mean, it will be more convenient, more compact to have the following. Okay, so what do we get? 9 minus 8 is that a 1 minus 2i. So again, when adding, subtracting complex numbers, we add or subtract reals with reals, imaginaries with imaginaries, like terms, you know. And then what about 7 minus 8? Is that negative 1 minus 2i? The other two elements remain the same. And let that be equal to 0, to the 0 vector. All right. So, okay, guys. Yes, this looks ugly because do you really want to reduce a matrix with complex numbers? So, do you want to divide the first row by 1 minus 2i and then having to divide by the conjugate of this? No, do that. Don't do that. Don't waste your time. Again, we're going to get a system right here whose number of solutions is infinite. So just grab the rows and turn it into its corresponding algebraic equation. In other words, decode one of the rows into the equation. Okay. Now, which one do we do? Which one? Well, whatever is the easiest one. And I like the first one because the second element, the 1 2 element, it's either a 1 or a negative 1. You can do the second one if you want, that's fine. But I'm going to do the first one. Let me highlight it just so you can see which row I'm turning into an equation. Okay, so I'm turning this into the following equation. 1 minus 2i v1, okay, this is the coefficient of v1 minus v2 equals to, what is that? 0, isn't it? Now, solving the equation, actually, okay, do you want to solve for v2 or do you want to solve for v1? Which one is easier to solve for? For v2, right? I mean, because if you solve for v1, then you will have to divide by the complex number, multiply numerator and denominator by the complex conjugate, which is not hard to do. However, it's not efficient for our purpose here. So that means v2 equals 1 minus 2i v1, okay? Now remember how in the previous couple of exercises, I believe for both cases we gave any number to V2, I believe. In this case, we're going to do it for V1. So there's no rule about giving it to V1 or to V2. It doesn't matter. Okay. So again, we're going with whatever is more convenient for us. So let V1 equals to 1. Okay. Let it be equal to 1. That means V2 equals to 1 minus 2i times 1, which is simply 1 minus 2i. So now we have the components of the eigenvector corresponding to a plus 2i. And that is, so the vector we're looking for has components at v1, v2, which are, what are they? 1, 1 minus 2i. All right. So yes, eigenvectors can also, or I mean, vectors can also be complex. How are we going to use these eigenvectors when solving the systems of equations? Well, this is like the funniest part of the topic, you know? Okay, you'll see. Okay, so we have the eigenvector for lambda 1 equals to 8 plus 2i. How about we do the one for lambda 2, which is 8 plus 2 minus 2i, rather. And I mean, it doesn't matter which one is your lambda 1 and which one is your lambda 2. It doesn't matter. As long as you don't mix and match eigenvector with the eigenvalue, so that's fine. Okay? So 2i. All right. So what do we do? Similarly, a minus 8 minus 2i in this case times the vector v, let that be equal to the 0 vector. As a system of equations, what do we do? 9 minus the eigenvalue, that is 8 minus 2i. Now be careful with signs. And then 7 minus 8 minus 2i. And that'll be negative 1 and 5. And let that times the vector v1, v2, and let that be equal to the 0 vector, which is 0, 0, the 0 column, the vector. I mean, basic arithmetic. 9 minus 8 is that 1. Yep, that's 1 minus minus. Careful, plus 2i. Okay, 7 minus 8, negative 1. Minus minus, another minus minus, that's a plus 2i. All right? The other two elements just remain the same, negative 1 and 5. As an augmented matrix, again, which is more convenient to do, I mean, unless you want to do all the steps, multiply the matrices, I don't see a need for doing that, right? So what is that equal to? Okay, again, do not reduce the matrix by hand. Don't do it. Don't waste your time. Don't waste valuable time doing that. Just select your favorite row, which again, how about the first row looks like the easiest one to decode into an equation? It's the easiest one. That means 1 plus 2i v1 minus v2 equals to 0. And just like the previous case, I'm going to solve for v2 because that's the easiest one to solve for. So v2 equals to 1 plus 2i v1. All right. That means let's let v1 equals to 1, your favorite number, but keep the simplest one, right? A number that doesn't give you any trouble, right? So that means v2 equals 1 minus 1 plus 2i times 1, which is 1 plus 2i, okay? So the eigenvector v with components v1, v2 will be, 1, 1 plus 2i. Okay, guys, compare these two vectors. This eigenvector that I have boxed right here. What do you notice about those two vectors, the eigenvectors here? Okay, what do we call positive, negative thing? Yes, you're right. But that's a specific name for this. Hmm. Starts with a C. So guys, these vectors, when it comes to eigenvalues that are complex eigenvectors, the eigenvectors will be complex conjugates, right? That's what it is, okay? And all right, so what we have an example of each. So one with with distinct eigenvalues, one with repeated eigenvalues, and one with complex eigenvalues. What do we do for each? Well, now let's increase the dimension and find the eigenvalues for A equals to whatever this big matrix is. Then find the eigenvector, only the one corresponding to the largest of the eigenvalues, because guys, work the more increasing the dimension, the problem becomes more tedious. And in a situation like that, let's say you're working with a 5 by 5, a 7 by 7 matrix, just use MATLAB or Python or Maple, uh, any uh, any computer system to get you to help you get the results we're looking for. Okay. Well, so let's say A. Come there you go. So A, which is no, A minus lambda I. That'll be subtract lambda from the elements along the main diagonal. 3 minus lambda, 5 minus lambda, and 2 minus lambda. The remaining elements remain the same. We don't do anything to them. All right? Now, to find the eigenvalues for this, what do we do? Set the determinant of this and write the determinant and set it equal to 0. That's to give us the characteristic equation, which is the equation that will give us the eigenvalue. Okay, how do we evaluate that determinant? Do the diagonals. Remember Sarah's rule in which we repeated the first two columns? But this is a triangular matrix, right? Remember that that extra. Well, it's not a trick; it's an actual definition in linear algebra. Every time you have a triangular matrix that is non-zero elements along the main diagonal, and either the upper or the lower elements are all zeros, well, that's a triangular matrix. Only go with the product of the elements along the main diagonal. So that's going to make our work a lot easier to do. So that'll be 3 minus lambda times 5 minus lambda times 2 minus lambda. Let that be equal to 0, and come on. This is already factored for us, which is great. So we got the eigenvalues very easily. So lambda equals to 3, lambda equals to 5, and lambda equals to 2. So whenever we get triangular matrices, especially if they are 3 by 3 or bigger, ooh, those are our best friends. No, what I mean, if our purpose is to get the eigenvalues, of course, all right? Okay, well, So they're asking us the eigenvector corresponding to the largest of the eigenvalues. That is for lambda equals to 5. So let's go for it. Okay, so for lambda equals to 5, we want to solve the vector equation. That is a minus 5i times v equal to the 0 vector. All right, that is, so only subtract along the main diagonal. I mean, we have the lambda here, right? Pretty much pre-set up for us. So 3 minus 5, and then 5 minus 5, and what's the next? 2 minus 5. So 0, 0, 0, 6, 7, negative 4. That times v1, v2, v3 equals the 0 vector. Okay? All right, well, let's simplify this. And also, at the same time, I would like to, I would like to write as an augmented matrix. So 3 minus 5 is that negative 2, 0, 0, 0. And 5 minus 5 is a 0, 6, 7, and then negative 4. And then finally 2 minus 5 is that negative 3. And augment it with the 0 column, the 0 vector as a column. All right? Okay, well, let's this one. So what do we have here? So guys, if we decode this into equations and not to keep it into a matrix, let's rewrite this. Okay, number one, the third row. Okay, the third row tells us that v3 equal, I mean, negative 3v3 equals to 0, right? That means v3 equals to 0. Also, the second row tells us that negative 4 v3 equals to 0, which is just another way to say v3 equals to 0. This is the same statement, just stated different. Okay, so what about the first row? The first row tells us negative 2 v1 plus 6 v2 plus 7 v3 equals to 0. But guys, what do we know about v3? Isn't that equal to 0 already? So that actually reduces the problem because one equation, three unknowns, big problem. Two unknowns, not the biggest problem. Okay. Now, this would be negative 2v1 plus 6v2 equals to 0. Okay, so v3 is already 0. Now, here's where we're going to use the trick again. This time, I'm going to solve for v1 because if I solve for v2, that's going to give me fractions. Okay, I mean we could do that, but that's fine. I'm going to solve for v1. Negative 2 v1 equals to negative 6 v2. Divide both sides by negative 2. v1 equals 3 v2. Okay. Now that, so guys, we already let me preset. Let me rewrite the eigenvector. What we have so far. Okay. The third component is already 0, isn't it? We just need to figure out the other two. How? With this equation here, in which we will let v2 equals to 1. That means v1, I mean, equals to 3 times 1, which is 3. So 3, 1, 0. That's the corresponding eigenvector for the eigenvalue equals to 5. As you can see, guys, it's quite a process for a 3 by 3. All right? It's quite a process. So, well, that's why I'm only doing one, okay? It seems like this is the end, isn't it? All right.